So here we have two blocks connected by a string that are pulled across a horizontal surface by a force applied to one of the blocks. It says the coefficient of friction between the blocks and the surface is 0.25. If each block has an acceleration in 3 meters per second squared to the right, what is the magnitude of F of the applied force in newtons? All right, so pretty straightforward. Here are two blocks that are being pulled to the right. The force that is acting on the system is touching the box on the right here, or block on the right here, which is 3.8 kilogram. Okay, so let's go ahead and draw your free body diagrams out for these types of things so that the physics that you set up is proper. All right, this force here, the applied force, is a diagonal pointing in the northeast direction. So I'm going to draw my f of x pointing to the right, and then my f of y is going to be pointing upward. All right. The problem didn't tell me which is mass 1 and which is mass 2. So as you practice, make a choice for yourself. I'm just going to call this 3.8 kilogram M1. You can call it M2 if you want. It doesn't matter. Just be consistent with the choice you make in terms of subscripts. All right. If I call this M1, I'm going to draw f of g. F of g, this is f of g1. It's important that you differentiate between the f of g's because you have two blocks. So make sure you use subscripts A, B, or 1, 2. I'm just going to use 1 and 2 here. Fn1 is going to be pointing up. So while the weight of the box M1 here is going to push down on the surface pushes up on the box, creating a contact force. This is Fn1. I do want to point out, conceptually speaking, why this is not drawn to scale. I drew Fn1 smaller than f of g1 because if you look at M1, it is not accelerating upward or downward because it's to remain on the surface, the horizontal surface here. So I like to think of it, there are two arrows pointing upward. Here's Fn1, here's f of y. Both of these are pointing upward, but the sum of these two vectors pointing upward must equal to f of g1. Okay, which implies that Fn1 must be less than f of g1. For example, like if f of g is 10, this can't be 10. Like this can be 2. If this is 2, then this is 8. If this is 3, and this is 7. Regardless, Fn1 must be less than f of g1. So keep that conceptual concept in mind. So I made a note here. This is important. Fn1 is less than f of g1. A common mistake that folks might make is they assume that Fn1 is equal to f of g1, neglecting the fact that there is an additional fy component here. So this is kind of a trap set up for you, okay? Don't fall for that trap. Fn1 is not equal to fg1 because there is this additional y component acting on M1. Okay, now let's go ahead and move on to the 1.8 kilogram. I'm going to call this M2. The f of g2 is going to point downward. I drew f of g2 smaller than f of g1 just because it's 1.8 versus 3.8 kilograms. Again, not drawn on scale, but just a little smaller so you can kind of see that it should be, or what should be, okay? If f of g is pointing downward for M2, there's no additional forces in the y direction. It's just a contact force exerted by the floor onto the box. So I'm going to call that f of n2. While Fn1 is not equal to f of g1, for the second block here though, this trailing block here, Fn1 is equal to f of g2 because there are only two arrows. So the up arrow must equal to the down arrow for M2. So I made this statement. Fn2 is equal to f of g2. So as you practice, you just have to understand when Fn equals to fg, when it is not. Sometimes it's greater, sometimes it's less, okay? So don't fall for this trap set up for you. All right, here's f of k1. Fk1 is going to point leftward because the system is being pulled to the right, and it says that the system accelerates 3 meters per second squared to the right, which implies that f of k points against it. In this case, it would be pointing left. But if there's friction on M2 as well, M2 will also generate its own kinetic frictional force. I'll call that FK2. So as you can see, both these arrows are pointing leftward because they're acting against the system's motion. Okay. All right. Now that we have, I think, everything drawn out, let's go ahead and set this up. I'm going to set up the net force in the x direction equals to max, right? Because the system accelerates to the right. So therefore, if I expand this function out here, if you look at this diagram properly, fx that is kind of grown on the screen here, that is pointing right. fk1 is pointing left, and then you have fk2 is also pointing left. So I'm going to take fx, which is pointing right. I'm going to subtract it from fk1 and fk2 because both these vectors are opposing the applied forces of motion. So in the next statement here, I just have fx. Well, the angle that's given is touching the horizontal axis, so fx is cosine. So I did f cosine of 61 minus, by definition, f of k is mu k times f of n. But you notice here, if it's f of k1, I have to use f of n1. And likewise, f of k2 is mu k. The mu k doesn't have a subscript because the problem says that it's the same for both boxes, okay? So here's mu k times fn2. And then the mass on the right is, you're pulling the whole entire system, so it's just m1 plus m2. Or you can just write m total if you like. In this case, let's go and trickle it down. The first substitution I want to do, this way it doesn't confuse you, hopefully you're following along, is fn2. Well, if you look at this diagram, fn2 is pointing upward, and I stated earlier, if you look at m2 for my choice of subscript, fn is pointing up and f of g is pointing down. They have to equal in magnitude because there are no additional vertical components presented, okay? All right, so fn2 must equal to f of g2. So I did that substitution there. fn2, I replace it with f of g2. And then here, f of g2, I broke down into mass 2 times gravity, because by definition, f of g is just the mass times acceleration. And which mass? Mass 2, because this is f of g2. All right, so in the next line here, I highlight f of n1 because now I'm done with fn2, right? I already placed fn2 out. The only thing I really have left unknown here is f of n1. So I want to look at m1 here. So if you listened earlier, I said fn1 plus fy. You have two arrows pointing up. The two arrows pointing up must equal to everything pointing down, but there's only one arrow pointing down. So in my work here, I want to make the statement fn1, which is pointing up, plus fy, which is also pointing up, must equal to f of g1, which is pointing down. And the negative sign's already been taken care of for you here. Now, if I were to solve for f of n1, because that's what I need here in blue, and highlight in blue, I need f of n1. So when you get to here, you just have to know what is that you're isolating for. I need to isolate for f of n1 because I need it. And then to get rid of fy, I'll subtract it on both sides. So I'll bring this positive to the right side of the equal sign, which changes sign. So here, fn1 is m1 times g, because f of g1 is mass 1 times gravity, minus fy. But fy is just f sine of 61. Fy is the opposite leg, because once again, the angle here given is touching the horizontal axis. So y is sine and x is cosine. Okay. So now that I have that, I can just substitute it in for f1, and I can just carry everything down. I'm just going to keep everything in variable form real quick, just in case you're asked to derive expressions. Here's f. I carry down cosine of 61. Mu k is left in the front. But I want to substitute out fn1 using parentheses. So it's important that your habits are super good. Otherwise, when you substitute without parentheses, you're really just wasting a lot of time and effort. Okay. So in parentheses, I substitute out fn1 for m1g, which is what this is, m1g, minus f sine 61, minus f sine 61 degrees. And I'm going to close parentheses. Everything else I haven't changed, so I just carry it down. All right, so here I'm just going to plug values in now, because now I have everything really, right? I know what mu is, I know what m is, I know what g is. The only thing left in the statement really is just f. Okay, so I plugged everything in. If you punch in cosine of 61 degrees, you'll get about 0.485. I round off to 3 decimals here, so my answer is not too off since these numbers are small. So 0.085, and then here's f times f minus mu k is 0.25 because that was given. If you take m1, which is 3.8 times 9.8, you'll get 37.24. I left the units out here because I'm running out of space on my screen. Here, if you punch in sine of 61 degrees, you get about 0.875. And don't forget to carry down the f, right? Here is just f times sine of 61, but sine of 61 is just this coefficient. So I like to write my coefficients out front. 0.875 times f minus mu k is 0.25, mass 2 is 1.8. So if you take 1.8 times 9.8, you'll get 17.64. That's where it came from. And then m1 plus m2, well, if you look at the diagram earlier, 1.8 plus 3.8 kilogram is just 5.6 kilograms. A is just 3 because it was given, and it's positive because it sets to the right. Now, I made this note, okay, because again, you don't want to do all this work and then kind of have a lot of algebra hiccups. Hopefully none, but if your algebra sucks, this is where you're going to be wasting a lot of time and effort. Here, you have 0.25 that's negative. This is negative 0.25, and you got to distribute this. So make sure you distribute. Make sure you look at the sign in front of the coefficient. So negative 0.25 times 37.25, and then you have negative 0.25 times negative 0.8. So a negative times a positive is a negative, but then a negative times a negative will give you a positive. So make sure you distribute the negative sign, otherwise you will have your signs off, and your signs off, everything else is going to be wrong, okay? So in my work, I carry the 0.485F down because I haven't touched it. And then here, negative 0.25 times 37.25 gives me a negative 9.31. And then negative 0.25 times negative 0.875F gives me a positive 0.219F. Okay, so make sure you keep that in mind. All right, other than that, if you punch in negative 0.25 times 17.64, you get negative 4.41. And then you do 5.3 times 5.6 times 3, you get 16.8 on the right side of the equal sign. And here, really, we're just going to combine like terms. This first term has an F. This third term here has an F, and everything else are just plain coefficients. So let's go ahead and combine everything. I'm going to take this 0.485F. I'm going to add it to 0.219F, which gives me a positive 0.704F. And then here is a negative 9.31. You have another negative 4.41, which makes a bigger negative. So if you add those two negative values, you get negative 13.72. The right side I haven't touched, so I'm just doing this step for step for you. So hopefully you can keep up with the tedious algebra here. Well, how do I get F by itself? I need to get rid of this 13.72. So moving negative 13.72 to the right will make it positive. That will get F by itself almost. So if you take 16.8 plus 13.72, you get 30.52. Well, to get F by itself, you would divide both sides by 0.704. And if you do that correctly on your calculator, you just get a value of 43.35 newtons. Okay? And that is your answer. And it says, what is the magnitude of the applied force? So that's done. And if it doesn't say magnitude, you would express it as 43.35 newtons, 61 degrees north, east, or 61 degrees above the positive x-axis. But I like the word magnitude here, so I'm just going to be done with this one. All right, I hope that helps. Keep track of misconception and where errors could possibly be made. Good luck. Stay nerdy.